Okay, so this is scientific notation part 1, but we are doing part 2. So just a quick review of part 1. This is back from Friday. Remember, scientific notation was a way of writing really large numbers and really small numbers in a nice little convenient shorter version, because mathematicians are lazy. Apparently scientists are too. Okay, so what we do is we write those really large numbers. For example, 56,900,000 by writing it as a product of two numbers. The first number is a number that's between 1 and 10. And the second part of the number is a power of 10. So we have two parts. And it looks like this. This first number has got to be between 1 and 10. And if you notice, 56,900,000 is too big.
5.69. 5.69.
So we make it 5.69, but because we moved the decimal, we have to state that however many times we moved our decimal, that's going to be the power of 10. So we moved it 7 times. But that's when it's a really too big number. But when it's a really too small number, like say this one, it's going to have a negative exponent. So this would be 3.25 times 10 to the 1, 2, 3, 4, 5, 6, negative 6. Because it's too small, it's negative 6. Now, how I remember positives versus negatives is I like to think of money in my bank account. If I had $56,900,000 in my bank account, I would have a very positive attitude. If I had $0.0000325 in my bank account, which isn't even possible because that's like less than a
cents.
Yes, it's like so small, it's like, yeah, I would be really sad. It would be a
That's
very
like
negative thing.
A millionth of cents.
Well, at least it's not the negatives.
True, that means I don't owe anybody, at least. All right, so you guys, are you good with that basic understanding of scientific notation? Awesome, because now we're going to do operations with scientific notation. So the first thing we're going to do is we're going to multiply. We're going to multiply two numbers that are in scientific notation. So we have 7 times 10 to the second times 4 times 10 to the fifth. Now let me just remind you of a property that we've talked about in the past. We talked about it last year. You didn't talk about it with me, but your other teachers. It's the property of the commutative property of multiplication. The commutative property of multiplication says it doesn't matter which order you multiply things in, you still get the same answer, right? So you can rearrange all the numbers to be multiplied in any way you want to that makes it the easiest to multiply. So that means that 7 times 10 to the second and 4 times 10 to the fifth can be rewritten as 7 times 4 times 10 to the second times 10 to the fifth. Now, Sans, what's 7 times 4? Absolutely. And remember the rules of multiplying exponents. If they have the same base, what do you actually do? Add the exponents. So this is really 28 times 10 to the 7th power. Now that was pretty easy, right?
You don't have to solve it.
Well, as long as the answer is in scientific notation, we're done. Is it in scientific notation? Zoe says no, and she's absolutely correct. Because 28 is too big. So what we're going to do is we're gonna set this guy aside for now. 10 to the 7th, we're gonna set aside, and we're gonna focus in on 28. We're gonna write 28 as a scientific notation number. That is 2.8 times 10. How many times did we move it? Once. Now let's bring back that 10 to the 7th we had earlier. Hey, these guys have the same base. So it's 2.8 times 10 to the 8th power. All right, now, wasn't that a whole lot easier once I rearranged it? Yeah, kind of was. All right, I'm going to go ahead and erase this out of here. So those of you who are taking notes, if you've got them all down, I'm going to make some more room because I need room for letter B. Because we're going to do the same thing for letter B. We've got two scientific numbers, notation numbers that we need to multiply. Now, I think multiplying these are much easier than putting them into standard form and then multiplying and then having to change them back into scientific notation. All right, so we have, I'll write it bigger, 9 times 10 to the negative 6 times 7 times 10 to the negative 9. How do I want to rearrange this, Alec?
You're gonna wanna put the tens together and then maybe multiply the 9 and the 7.
Yep, we're going to multiply the 9 and the 7. That's going to be our number out front. All right, Dustin, what do we get from 9 times 7?
9 times 7, that would be 63. I just thought it was tricky.
And then when we have our 10 to the negative 6 and 10 to the negative 9, Brecken, what do we get from those? What do we do when we put these together? What do we do when we have a power times a power? What do we actually do with the powers? We're going to add them together. We're going to add the powers together. So negative 6 plus negative 9. All right, so you guys, these two we multiply. These two we add. These two we multiply. These two we add. So it's negative 6 and negative 9. So we negative 15, but I can't leave it like this. What's wrong with it, Tyrese? It's got to be 6.3. So let's take this guy and change it into scientific notation. 6.3 times 10 to the first, right? Because we moved it one spot over. But now I have a 1 and a negative 15 that I have to add.
Yes.
Yes, Abby. Right, so we have 6.3 times 10 to the negative 14th power. All right, you guys, that's how we multiply numbers in scientific notation form. You multiply the whole numbers, you add your exponents, and then you might have to tweak it after you get done doing that. All right, let's see the word problems because word problems are so much fun. All right, so we have a big guy here. We have a human body contains about 3.2 times 10 to the 4th microliters of blood for each pound of body weight. Each microliter of blood contains about 5 times 10 to the 6th red blood cells. We need to find the approximate number of red blood cells in the body of a 125-pound person. Whoa, that's a lot of stuff we have to do. Ethan, what do we have to do with these numbers? We've got this guy. That's how many microliters are in microliters of blood are in each pound of one person. But we have a 125-pound person, so what should we do? We're going to multiply 3.2 times 10 to the fourth times 125, but that just tells us how many microliters. Now we need to find out how many red blood cells. So we need to multiply this by 5 times to the 10 to the 6. Right, well, we're going to change 125 into a scientific notation number. How's that? So this would be 1.25 times 10 to the second. All right,
True.
because it was 125, I moved the decimal over twice. Okay, now I'm going to rearrange. So I have 3.2 times 1.25 times 5. So those are all our non-powers of 10. Then I'm going to put my powers of 10 in the same area. So 10 to the fourth times 10 to the second times 10 to the sixth. Okay. Now we're going to take 3.2 times 1.25 times 5. I think Zoe's got this. All right, so we have 20. Now we're going to have our 4 plus 2 plus 6.
12.
But now 20 is too big. So I have to move it over. So I'm going to make that 2.0 times 10 to the first times 10 to the 12, which is going to be 2 times 10 to the 13. So that's how many blood cells are, red blood cells are in a 125-pound person, approximately. Okay, was that a lot of work?
Yes.
Yeah.
Nah, wasn't that bad.
Sweating.
Okay, so you guys, I have to go ahead and erase all of this so that I can make room for the next one, example 3, because we definitely have to do example 3 because now we're not multiplying anymore. We have a power. How do we do a scientific notation to a power? Oh, I don't know. We're going to use the power rules that we had when we did exponents because it's all very similar. Okay, so all objects, even resting ones, contain energy, even a raisin. The raisin has a mass of 10 to the negative third kilograms. The expression 10 to the negative third times 3 times 10 to the 8th squared describes the amount of resting energy in joules the raisin contains. We need to simplify it. What happens when we have, okay, hold on a second. Let's go back in time when I was gone and you guys were here to something that looked like this. What do we do to simplify that power mesh? We do 3 times 4, but do we do anything else with that 4? Ella? It has to go on both of those bases, right? So that gives us 2 to the 4th, a to the 12th. So 2 to the 4th is 2 times 2 times 2 times 2. So this would be 16a to the 12th. So you raise this thing to the power and you multiply the powers. Okay, that was our rule. This is supposed to be review of something we learned last week. So let's hold off on that 10 to the negative third. Let's pretend it doesn't exist for now because we have to get rid of this power. Where do I put that power? Nicole, where should I put that power? Scott, where should I put that power?
You should put it by the 3.
Let's put it by the 3, so we have 3 to the second. Cooper, where else should I put the power? Times it by 8. So we have 3 to the second, which is what? 9. So we have 9 times 10 to the 16th power times 10 to the negative third. So now what do I do to simplify? Cole? What about these two?
Oh,
They're the same.
so is that a -3?
Yeah,
So it's gonna be 13.
absolutely. 9 times 10 to the 13th
Well, you're
power.
a cool cat.
No.
Okay, you guys. So that was how we multiplied, and that's how we do powers. But now we're going to divide. So how many of you think Jacob was right? That this is so hard?
Jacob.
Oh, you guys.
Jacob was as right as a triangle. That is right.
Okay, well, we're gonna do some division now. Now, when we had multiplying, we multiplied the big numbers and we added the exponents. So this time, we're gonna divide and subtract. So we have 2 divided by 8. What is 2 divided by 8? Not in fraction form, put it in decimals. .25, right? What's 3 minus 8? Yes. -5. So we have 0.25 times 10 to the negative fifth. This in scientific notation, it is not, it's too small. So we're going to take 0.25 and we're going to change it to 2.5. But since it was too small, we moved it one place, it would be a -1. With the 10 to the -5 that we already had, when we put them together, what do we get? (2.5) times 10 to the -6. Okay, so Dustin, what are you doing? Put your iPad upside down, please.
Dude, was that the new Winnipeg montage?
Cole? Okay. So let's look at this last one before we get to the word problem at the end. All right. We have 7.5 times 10 to the 12 over 2.5 times 10 to the -4. We're going to divide and subtract. Yes.
Does that thing up there for the middle one say cold test?
Chapter 6 test.
No, for pre-cal.
Chapter 6 test.
Yeah,
On Thursday.
Yes.
chapter 6.
Yes. Here, let me.
When she said 6 times.
1. It doesn't count.
It says CH 6. Test.
All right, now that we figured that one out, we're gonna take 7.5 divided by 2.5. And that's our first number. What is it? 3. We're gonna take 12 minus -4. What happens when we subtract a negative? So we get,
Plus or minus.
how easy is that?
Pretty hard.
Not really. Okay, the last one is a word problem. Let me erase this piece of information. It's kind of fun to erase this.
Kind of like you're a kid doing one.
Miss Paul,
Yeah,
I think if you draw like a big circle around it, it'll erase everything.
I have tried that because we've used this with pre-calc. We tried it and it doesn't work.
That's kind of special, boy.
Yes, it touched the.
Yeah.
Tap the center after you do it.
You what?
Tap the center after you make the circle.
True.
Oh, she was looking up.
Faster.
Mm.
Faster.
It doesn't work.
It's a glitch. You have to go fast.
Okay, remember, this is like a really old iPad,
That's
so it's
true.
probably
Your
that.
iPad can't handle the speed.
All right, so you guys, let's finish this up, so you have some time. In 1998, the total amount of waste paper and cardboard recycled in the United States was 35 million tons. The population of the United States in 1998 was 270.5 million. We want to know how much paper did each person recycle. So we want to do paper, paper divided by people to find out the paper per person rate. Okay, so 35 million is what as a scientific notation number? Isabel, do you know what 35 million looks like as a scientific notation? I always have to write it out. I think
Is
it's
it
7.
7.
Okay, so we have 3.5 times 10 to the 7th. And then on the bottom, we have 270.5 million. So I want to say this would be one more, right? It'd be 8.
No, it's 7.
It shouldn't be. Right, because this is in the tens and this has
There's
100s.
There's 6 zeros.
Okay, there's 270.5 million. Looks like that.
That's some big number.
So it's-
That should be
it
8.
should be 8. Okay, so we're gonna take and divide these two, so 3.5 divided by 2.705. Should be 1 point something, yuck, numbers, what is it? Huh, we're gonna round to 1.3.
Okay.
So we get 1.3, we're gonna subtract these numbers. And that's how many tons per person. Okay, you guys ready for your homework? Do you have any questions over what we just talked about?
Yeah, like you said, it's not-
That's not wrong.
Where's VRS?
O-N,
That's an M.
O-N.
That's an M.
Yeah,
Tyrese?
Your name's gonna be on the boat.
Okay, well, it's not.
Tyrese, you shall walk this way.
Hey, you guys, it's page 403, 23 through 33, 42, 43, and 49 through 52.
You